This is a video introducing the A-level chemistry topic of covalent bonding, including dative, or it's sometimes called coordinate covalent bonding. As we saw in our introductory video, at GCSE we've had this idea that covalent bonding is something that happens between non-metal atoms, but this is actually a bit of an oversimplification because there aren't really three distinct types of bonding. There's a sort of spectrum where things can be more covalent or more ionic or more metallic. So at GCSE we said that covalent bonding happened between non-metals, but it would be truer to say that it happens between elements that have similar electronegativity. So if you have two non-metal atoms that are identical, say two hydrogen or two chlorine, then obviously that will form a covalent bond. But also there can be elements that are quite similar in electronegativity and they will still have a purely covalent bond. So there are actually a list of numbers we can have that describe the electronegativity here. And a kind of general rule of thumb, which isn't written down in the A-level specification, but which I tend to use, is that if the difference in electronegativity is less than 0.5, then that is just a straight up covalent bond. If it's still less than 1.6, but it's a little bit bigger, then that's what we're going to call a polar covalent bond, where the electrons are slightly more attracted to one of the atoms. And once it's over 2, then we describe it as ionic. So obviously that leaves a little bit of wiggle room in the middle, where we have what we call substances that are ionically bonded but have covalent character, for instance aluminium oxide. But we'll worry about those in a different video. So a covalent bond is a shared pair of electrons, and we can display this as a dot and cross diagram, but also we can display it as just a single straight line. And at GCSE you would have met the idea of small covalent molecules, or they might have been called simple covalent molecules if you used a different exam specification, and also giant covalent structures like diamond and graphite and graphene and silica and fullerenes. And so you would have done some work at GCSE about their different properties, and you kind of still need to know all that stuff at A-level. So at GCSE you would also have met the idea of multiple covalent bonds, specifically oxygen with a double covalent bond and nitrogen with a triple covalent bond. And if we want to show this using the line format, then we do a sort of equal sign for a double bond and then 3 horizontal lines to represent a triple bond, as you see in nitrogen. Just like at GCSE, you need to be able to discuss the properties of these small covalent molecular substances and how they are distinct from giant covalent structures like diamond and graphite, or ionic substances like sodium chloride. And this is one of the bits of the A-level syllabus that's basically exactly the same as GCSE, but to be honest with you, a lot of people didn't really understand it at GCSE, so it's worth us talking about again. So the first thing that you need to know is that the small covalent substances are usually gases or liquids at room temperature, and even where they're solids, they tend to have comparatively low melting and boiling points. So it's quite easy to melt them or boil them. And the reason for this is because they only have weak intermolecular forces between the molecules. So if you look at these 3 water molecules I've drawn, you can see that they've each got 2 strong covalent bonds between the hydrogen atoms and the oxygen atoms. And those bonds are very, very strong. But when ice melts to make liquid water, or when water boils to make steam, it's not those strong covalent bonds between the atoms that are breaking. What's happening is this very weak intermolecular force between the separate molecules, which I've represented here with the green lines, that is being overcome. Now when we get a little bit later in the A-level, we're going to talk about different kinds of intermolecular forces and how they could be weaker or stronger. But for now you just kind of need to know that where you have small covalent molecules, it's the force between them, not the bond inside them, that is being overcome. And when we're describing this, we want to talk about the fact that it takes a lot of energy to overcome it, or in this case, it doesn't take very much energy at all. We don't want to just be talking about it being easier or harder. We need to link it back to energy. Also, if everything else is the same about a molecule, say if we had a series of alkanes, for instance, then the larger the molecule is, the stronger those weak intermolecular forces will be. Now, there are lots of things that can affect the strength of a weak intermolecular force, so I'm only talking about molecules that are otherwise very similar. That's why alkanes are a nice example. But as long as the molecule is very similar, then the size of it is going to determine the size of that weak intermolecular force. And that's why you would have learnt at GCSE that within a fractionating column, you have your smallest alkanes with your very low boiling points at the top of the column, and then your larger alkanes with much higher boiling points further down the column. The other thing you need to know about small covalent molecules is that they can't conduct electricity. And the reason for that is that the molecule doesn't have an overall electrical charge. So you should have met at GCSE the idea that pure water, if you have some distilled water, it doesn't actually conduct electricity, even though in popular culture we always think of it as being able to conduct. It's actually the salt ions that are dissolved in the water that do the conducting. Anytime that you have an uncharged overall molecule, that can't conduct electricity. So here's a typical example of an exam question. Explain in terms of bonding why the boiling point of chlorine is very low. So I'm going straight back to my GCSE knowledge, going chlorine, that's a small covalent molecular substance. So it has weak intermolecular forces between molecules, and these require very little energy to overcome. Again, it's important that we're saying it requires very little energy. We're not just saying that it's easy. Let's be scientific about this. Here's a slightly more challenging example. We're asked to explain in terms of bonding why the boiling point of fluorine is lower than chlorine. So again, I know that these are non-metals, I know that they're symmetrical molecules, so they're going to be covalently bonded, and I know that the force that's being overcome is this weak intermolecular force. So even if I don't know anything else about fluorine and chlorine, I'm probably going to get a mark for mentioning the weak intermolecular force. And then if the boiling point of fluorine is lower, that tells me that that force is weaker. So the weak intermolecular force between fluorine molecules is smaller than that between chlorine molecules, and therefore it takes less energy to overcome. You also need to know about a special example of a covalent bond, which is called a coordinate bond, or sometimes it's called dative covalent. And this is a bond where both of the electrons in the covalent bond have come from one atom. So it's still a regular covalent bond. It's still a shared pair of electrons between two atoms, and then there's a sort of electrostatic attraction between the electrons in the bond and the nuclei of the two atoms. But the difference is here that both of those electrons have come from one atom. So that atom used to have a lone pair, and it's just contributed that lone pair to the bond. The other atom in that bond is going to be something that's electron deficient, something that doesn't have enough electrons. And once that bond is formed, you can't sort of look at it with a microscope and see, oh, these electrons came from this bond, but we just know that it's formed in a certain way, and therefore we give it a slightly different name. And it's represented, you can see here on my ammonium ion that I've drawn, one of the bonds, instead of being a little straight line, is an arrow. And that arrow shows us where the dative bond has formed, and that arrow points to the one that has accepted the electrons. So in this instance, the nitrogen in an ammonia molecule had a lone pair, and that lone pair has been shared with a hydrogen ion that didn't have any electrons at all, and so the arrow goes from the nitrogen to the hydrogen. So we might have a question that asks us to define the meaning of a covalent bond, and that's a shared pair of electrons, or that asks us to define the meaning of a dative bond. So that's a shared pair of electrons where both of the electrons have come from the same atom. Finally, we also get slightly wordier questions like this one. So an ammonia molecule reacts with a hydrogen ion to form the NH4+ ammonium ion. And to be honest, there are only really a couple of examples of dative bonding at A-level, so this is the one that you're most likely to encounter, and you should really recognise it straight away. Name the type of bond formed in this reaction. Well, obviously that's going to be a dative covalent bond, or you could call it a coordinate bond as well. And explain how this type of bond is formed in the NH4+ ion. So the nitrogen atom inside the ammonia molecule donates a lone pair of electrons to the bond, and that is shared with the hydrogen ion. I hope that was helpful. Thanks for watching, and don't forget to subscribe.